Okay, so we're going to talk about solving trigonometric equations. There's some different ways of doing these in terms of what your domain of your solution set is. Because they're periodic functions, if we say here like solve for all possible solutions, you're probably going to have an infinite number of solutions. Okay, or a lot of times it'll say solve for solutions between 0 and 2 pi. When you do the delta math this evening or tomorrow, that's what you're going to see. It's going to just the ones between 0 and 2 pi. And we'll kind of work with how those different sets work. But just to kind of think about this before we actually look at solving it, this is just the sine of x equals 1/2. Now if we think back to our graphs, we know that the sine of x will look like this, and it just keeps going forever in both directions, correct? And we know these maximums up here where y is 1. Right? So if you think about what the line y equals 1/2 would look like, you see there's going to be a bunch of solutions, correct? There's actually going to be an infinite number of solutions. So that we have to just find a way to write that, to kind of do that. But now we don't really use the graph, but that's just sort of an idea of what's going on here. Is because it is a repeating function, it's just going to keep hitting and having solutions all over the place. And so for this one here, it's already isolated. We have the sine of x is equal to 1/2. The way I like to do these is I just think about my unit circle, and I think about the first rotation. Okay, so we go from 0 around to 2 pi. So in the first rotation, we know the sine is positive in the first and the second quadrants, correct? Yes. Okay, and for what angle is the sine going to give you 1/2? Yeah, 30 would be in degrees, but we're always going to do radians for these, so it would be pi over 6, right? So this right here, so one of your solutions is pi over 6, and then the other one's here in the second quadrant, right? So that'll be 5 pi over 6. Right there, they have the same reference angle, they have the same sine value. So the way we'd write this answer is we would say x equals pi over 6 plus, now, if you just went to pi over 6, that's a solution, but if you did a complete revolution, then went to pi over 6, that's another one, right? So we say pi over 6 plus 2 pi times k, right? That's adding a full revolution, where k is in the set of integers. And we'd also say x equals 5 pi over 6 plus 2 pi over k, where k is contained in the set of integers. You probably don't have to write that twice, but I did. Do you see how we would do that though? So it's just you're adding additional rotation or taking a rotation away. So that's what we're doing with that. Okay, so I think the next one we have here is very straightforward. If you want to try it, it just asks, using the same ideas, what is the solution of the tangent of x equals radical 3? Tangent of x equals radical 3. So go ahead and try that one, and we'll look at it here in just a second. Okay, so we have this, the tangent of x equals radical 3. So again, I'm going to think about my first trip around the unit circle. Right? Now I know that tangent is positive in the first and in the third quadrant. Right? That's the first and third quadrant. Remember, all students take calculus. So I also know that in the first quadrant, the tangent of pi over 3 is equal to radical 3. Right? And then what's it down here? It'll be 4 pi over 3. Now, it's fine to write this answer just like this one. It's perfectly acceptable. But there is another way you'll see this written sometimes. If you're checking your work sometimes, I want to make you aware of what's going on. So you could always just take the first location plus 2 pi k, second location plus 2 pi k for both of those k's contained in the set of integers, right, which is fine. This is a perfectly good solution. Now, with tangent and some other solutions, when we get more solutions, this will happen sometimes. But notice these are evenly spaced, correct? They're just pi apart from each other. So instead of writing these two statements, you could write x equals pi over 3 plus pi k, where k is in the set of k is contained in a set of integers. That's sufficient. That means the same thing, right? Because this one, when you do k, you're going to get like this point, and then you're going to get this point, and you're going to get this point over and over again. Where here, you're only going halfway around the circle for each new k value. So the first one's here, second's here, third's there, fourth's there. Okay, so is that making sense to everybody? How that would work? So, because if you look, if you put, say k is 0 here, you get pi over 3 and 4 pi over 3. But say that k is 1, you get 7 pi over 3 and 10 pi over 3. Right, and we could keep going there if you wanted to. Where in this one, you get pi over 3, and then you add, then you get, when you add 1 pi to it, you get 4 pi over 3. Then when you add another one to it, you get 7 pi over 3, and then you get 10 pi over 3. So it lists the same values. Now, if you're ever looking up solutions like in the back of a textbook, it'll probably write it like this, just because it's easier and more efficient. But if you write it like this, that's fine. It's a good thing. Okay, so here we have a more interesting equation. Those other ones there was nothing to solve, right? So, but in this case, we have 4 times the cosine squared of x minus 3 equals 0. We want this equation to look like the last one. So what we want to do is we want to isolate the cosine of x and have it equal. So cosine of x equals. So for this one, we're going to first, just like if it was 4x minus 3 and you were going to solve this, you would add 3 to both sides and divide by 4, correct? That's the same techniques we're going to use here. So we add 3 to both sides, divide both sides by 4. Now, we don't want cosine squared, we want just cosine. So we're going to square root both sides. Okay, now here the catch is, and I think there was one on the pretest too, is make sure that you, when you decide during the course of solving that you're going to square root both sides, one of those sides needs to get a plus or minus sign. So from here we're going to get the cosine of x is plus or minus radical 3. I could write radical 4, but I'm going to go ahead and write 2 anyways, just because that'll be easier to look at. So we get the cosine of x is equal to plus or minus radical 3 over 2. Does that follow for everybody? And then we think back to our unit circle. Now, if it's a plus or minus, we're going to expect to find, normally you would find 4 places around the unit circle, right? Because cosine is going to be positive in the first and fourth quadrant. It's going to be negative in the second and third. So let's see. The cosine is radical 3 over 2 at pi over 6, isn't it? And it's also an 11 pi over 6. So those are the 2 cases where it's positive. And then we know the cosine of 7 pi over 6. And, sorry, that's 5 pi over 6. 5 pi over 6. And 7 pi over 6, right? They all have the same reference angle. They all have the same distance from the x-axis. But again, this will give you radical 3 over 2, cosine of this. Cosine of 11 pi over 6 is radical 3 over 2. Cosine of 5 pi over 6 is negative radical 3 over 2. And the cosine of 7 pi over 6 is negative radical 3 over 2. So there's actually 4 positions in the first rotation where this happens. So to write this answer, we'll say pi over 6. Now, these are actually these are pi apart from each other, aren't they? So we have a couple options. You could write 4 lines or you could write 2 lines. It's up to you. So if you write 4 lines, it'd be plus 2 pi k, and then 5 pi over 6 plus 2 pi k, and then 7 pi over 6 plus 2 pi k, and then 11 pi over 6 plus 2 pi k, where k is contained in the set of integers. So you could write all that out, and that's fine. I don't have a problem with that if you want to write all that out. But whenever you get ones that are opposite each other, you can condense it. Instead of making it 2 pi k, you could just make it pi k. And it'll, just like we saw with the tangent in example 2. So, or you could write this as x equals pi over 6 plus pi k, x equals 5 pi over 6 plus pi k. K is contained in a set of integers. Okay, so that's the most efficient way to write it. Does it make sense that they're saying the same thing? Right, again, because k is just an integer, just a counting number. Now, these, it's not a case where you can't, here to here, this distance is 4 pi over 6, and this distance is 2 pi over 6. So they're not all evenly spaced. You can't get any more condensed than that, but this is either one of these answers would be great. Now just to, as you try the delta math here, it's going to say, it's going to give you the same problem, and it's going to say solve for x is contained from 0 to 2 pi. So this is actually the easiest one to get usually is when it just asks from 0 to 2 pi. So then it's just saying what x values in the first rotation would give you the solution. So we would make the same picture, do the same thing, but in this case your answer would be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. That makes sense? It's just asking for the domain of the answer. So, and then next time we're together, we'll look at when these domains get adjusted and how we can kind of work through that and some other things that can come up. Okay, so go ahead and let's take a look at some of these on the back here and just go and work on those with your neighbors, and we'll come back together and look at those shortly.